So this is my third BSides Winnipeg. I really like this conference. You guys do a very good job organizing it and putting it on. So I work for Cisco, and Cisco is a sponsor of this organization, but my talk is sort of an anti-marketing talk. So I'm mostly talking about how we as security practitioners get marketed to, and especially with regard to machine learning and other sort of magical security solutions. And I want to talk about sort of the marketing versus actual reality, and a little bit about how machine learning works. So it's about me. I've been doing this for a while. I'm a nerd. I like technology, that sort of thing. So I was standing in line yesterday to buy shampoo at a small little store, and I looked over and I saw a magazine, Time Special Edition. They have a special edition, Artificial Intelligence, the Future of Humankind. And then right next to it was Wired, in Love in the Time of Robots. When androids behave just like humans, how will humans behave with each other? Sort of, there's this strange belief, at least in the time that we live in right now, that we're on the verge of an AI revolution. That machine learning and artificial intelligence is just around the door to just changing everything. And you see warnings from smart people like Stephen Hawking and other folks, saying, we have to regulate machine learning, or we have to, be concerned about AI. And to be fair, there have been a lot of really impressive achievements out of machine learning in the last couple of years. So I have a couple here. So Google has a company called DeepMind, and they built a GAN, which is a generative adversarial network. So it's two neural networks that play off of each other. One tries to discern or identify what's fake versus what's real in a training set, and then the other one tries to fool it. And by carefully, feedback through a careful feedback mechanism between the two, you can generate sort of really interesting images. Like Google sort of marketed this as like dream images. So you can see like someone took a Golden Gate Bridge and it sort of dreamed in a whole bunch of bizarre artifacts. It looks like very much like a hallucination. And so here's another image generated by this, and really cool stuff. And this was a neat sort of marketing ploy by Google. And we've seen a lot of other things, right? So Google built some software called AlphaGo that for the first time can beat the world's best Go players. And Go was sort of the last board game that had resisted a computer attack. It's exponentially larger and more complex than chess in terms of a search space. And so computers were, only played as well as sort of low amateurs for a long time. And then via some recent developments in machine learning and developments in neural networks, now the computers are vastly superior to humans, not even close. Like the latest version of this software plays games that humans can't even analyze. Like humans look at the games and they don't know what's going on or why the computer played the way it does, but it beats even the best humans soundly. And we're actually, if we are on the verge of any sort of machine learning or AI revolution, self-driving cars is probably the first place that it'll come. And self-driving cars, there's a huge amount of computer vision research that has to go into self-driving cars. And there's all sorts of analysis of, what is an obstacle, what is not an obstacle, what has to be driven around, that sort of thing. It's pretty impressive stuff, and I think all of us are going to benefit from this over the next 5 to 10 to 15 years. So I think this is pretty exciting. And just a couple days ago, NVIDIA released a paper where they'd also built a GAN. So this GAN, you give it a training set of images, and so they gave it a training set of celebrity images, and then they built it so that it could generate new celebrity images that they could not tell apart from real celebrity images. And so if you look at these images over here, all of those images are 100% computer generated. Those are not photographs. And then these two images, the top and bottom image on the right-hand side, is some previous work where they'd attempted this, and you can see that if you get up close, it doesn't look quite right. It looks like there's some weird things going on. It's a computer-generated image. But we're at the point now where computer software can generate lifelike human images, and a human being honestly really can't tell them apart. And I think that's pretty impressive. And so in terms of marketing, this sort of demonstration is a really impressive, really cool demonstration. So we've also seen an explosion of digital assistants, right? There's Siri or Alexa or OK Google or Cortana or all the different digital assistants. And they're doing relatively impressive speech recognition and relatively impressive natural language processing and context-aware processing and context-aware search to provide results and perform tasks. So it has gotten to the point where even people like Elon Musk are saying things like, and I'll just try to read it off, and I can't see this very well, but he basically says that if you're not scared of artificial intelligence, you should be. And so with warnings like that, I think a lot of people are sort of genuinely optimistic that we're on the verge of an AI revolution, but they're also sort of a little bit hesitant or nervous about what this could mean. So those are very, very impressive achievements, some of the things that we've seen come out of artificial intelligence research or machine learning research. But almost all of these problems are sort of carefully selected problems where machine learning is particularly adept at solving these types of problems. And they're typically sort of engineered to give the biggest wow factor, generate celebrity images or generate dream images, or in the case of self-driving cars, that's probably the most practical of any of these demonstrations. The thing is about these problems is they are generally working off of complete information. And so what I mean by complete information, like in like a game like Go, you just look at the board, and that's all the information that there is to need. There's no hidden information. There's no hidden state. And even in the case of like a self-driving car, if a human being can drive a car simply by looking out the windshield and looking at the mirrors, and that's enough information, that's sufficient for a human to drive a car, then via LiDAR and cameras and a bunch of other sensing technologies that they're putting on self-driving cars also have, they're feeding the computer a complete set of information. I think actually in the case of self-driving cars, they're feeding the computer more information than a human being has available to them to sort of compensate for the fact that our brains are really sophisticated and the software is not actually that sophisticated. So they sort of overcompensate by feeding laser ranging data and a bunch of other data so that the car can do a job similar to how a human does it. The input to these systems is typically not generated adversarially. So when they're testing self-driving cars, there aren't a bunch of people sort of faking the sensors to make it think that a human ran across, or any other sort of adversarial attack to try to make the system fail. They're trying to make the system work sort of in ideal conditions. In most of these, whether it's a dream or generating a random celebrity image or playing Go or any of these sorts of things, there's often multiple right answers. So there's lots of potential choices, and some are better than others, but even if you don't choose the optimal choice, you choose the second or third or fourth or fifth optimal choice, you can still do a good job. And that's the case, like, even you'll see this in driving, right? Two different drivers will drive down the same road, and they'll do it differently. One will accelerate, one will brake, one will change lanes, but ultimately they both do it relatively safely. There's usually a bunch of ground truth available for these problems. So in the case of something like Go, it's tons of past games, and did the game win or did the game lose? In the case of generating celebrity images or other things like that, you have a data set. You have a set of real celebrity images that you feed to it. That's sort of the ground truth. But there's some underlying known truth to the data that you're feeding into the system in most of these. And then also, Most of these are working off of data that is in some sort of grid. And so Go is obviously a grid. But image processing for self-driving cars, that's a sort of a two-dimensional grid, right? Pixels along this way, pixels along this way. And even like natural language processing, like processing audio, time is one axis, and then they do a fast Fourier transform to translate the frequency data, or the amplitude data into the frequency domain, and then they do ultimately what is like a two-dimensional analysis on the data. So most of this data is grid-like. So that was some amazing stuff. And I think that the best is yet to come with regards to what we're going to see next in artificial intelligence research. And if you're a marketer, if you're trying to sell a product, why wouldn't you want to be associated with some of that really awesome stuff? I think most marketers rightly want to be associated with that. Now, this presentation is meant to be somewhat entertaining, so I have images interspersed through the presentation, and this image is Microsoft's marketing attempt where you upload an image and they've trained it on a bunch of different images that it knows about, and it tries to tell you what's in the image. And they did this sort of as a marketing ploy. They call it Caption Bot, and you upload images and it tells you what it thinks, and apparently that's a red apple. And so this is an example of being able to feed one of these networks data adversarially. You can just feed it images and you can manipulate the images until you trick it into giving you ridiculous answers. And so I've sort of adversarially fed it a bunch of entertaining images to see what it says. So machine learning, it's not artificial intelligence. That's a very popular term, a colloquial term. It doesn't really have a lot of meaning. Like, we don't even really know how to define intelligence, much less what is artificial intelligence versus non-artificial intelligence, right? So the computer science community, the research community, basically calls this machine learning, not artificial intelligence. And obviously, it's not magic. But when you see machine learning marketed, you typically see it marketed as AI, and there's always this air of magic. The computer can do something incredible. It's super smart in a way that even humans aren't type of sort of presentation to it. And it's just completely ridiculously wrong. But that's marketing for you. So there is one time that I've seen in Hollywood history where they've gotten something technology related right. And there was a movie from probably the late 80s, maybe early 90s, I don't remember exactly. It's The Hunt for Red October. And in the film, there's this computer on the submarine that analyzes audio. And it tries to tell them what type of submarine is chasing them, what is it hearing, that sort of thing. And the plot device is that the software was originally designed to analyze seismic events, earthquakes and other underground, like ground shifting events. And so when it hears like this special new propulsion system in the film, it doesn't know what it's actually hearing, and so it says it's a magma displacement. And so the Jonesy, the character who's talking about this, he's like, the software sort of runs home to mama. But this is a perfect example of how machine learning really works. Or the artifact of how machine learning works, which is that you give your machine learning model some set of data to train on as input, and then it can basically only recognize the things that it was already trained on. So in the case of Caption Bot, it had never seen Hal, but it had seen red apples, and a red apple seemed to be the closest thing that it had ever seen to Hal. That's why it said it was a red apple. And in the case of this film, magma displacement was the closest sound that it had ever been trained on that sounded like the Red October propulsion system, right? So this is one of the few times where Hollywood actually got something right. So machine learning is data algorithms and statistics. And the old name for machine learning was statistics. So even machine learning itself is sort of a marketing term that sort of the technical among us have sort of adopted, but it's really just statistics and algorithms on sets of data. Also, machine learning is probabilistic, and that's sort of a by definition statement, because when you have something that isn't probabilistic, we just call that a signature. We just call that a pattern match or a signature, right? So if you make something sort of highly specific to one thing and it has no probability of failing that thing, everyone just calls that a signature. So brace yourself for a whole bunch of ridiculous marketing. And I mean, there's just so many examples out there. I couldn't even begin to list them all. So I just pulled some snippets of text out from various different websites. And this is literally just copy and paste. So I mean, like multi-dimensional meta-anomaly analysis. Like, what the fuck is that? Like, or like cyber threat analytics. Like, well, I mean, maybe that means something, or correlation analysis engine, maybe that means something. But I think what they're trying to do here is they're trying to give you one or two words you recognize, and then one or two words you don't recognize, in hopes of using sort of your own creativity and your own smarts to sort of play the word mash game. And we all sort of, most of us, even though we're security engineers, we tend to be somewhat optimistic that that's real, it's not bullshit, right? So we try to come up with like, oh, well, maybe it's this, maybe it's that, and we always come up with sort of these really sophisticated ideas of what it might be. And I think that's why they like doing this, because everyone has a different idea, and everyone's idea is all it's really sophisticated and it seems really cool, and so that's why they keep on using crap like this. So I'm going to pick on some companies. This one, says user behavior analytics. This one, like I am anomalous, which I think is a fun play on words. And they list a bunch of, and I know you can't really read this, but the arrows are pointing towards ridiculous statements, or otherwise like sort of questionably meaningful statements. Like you can read it and you go, I'm not exactly sure what that really means. And so here's another one. And I'm just going to these vendors' websites and I'm looking at their products, and you just read the sentences that they're writing, and it sounds amazing. But I don't actually know what it is, right? It sounds like magic. So it goes on. Fort Scale, when you go into the details, like because the front page of bullshit wasn't enough, they have a deep dive where they give you more details about the bullshit, but the details are just bullshit themselves, right? So I'll pick on my own company here. My own company does this. We market it maybe a little bit less hard than some others, but there's all sorts of data anomaly, correlation analysis, detection, whatever, cyber engine, all over the place. And then of course Microsoft, it learns, it adapts, and all sorts of other things, even on Microsoft's own webpage. And I mean, like, this is a Windows computer, and we couldn't even get the screen mirrored right to the projector, yet somehow it learns and it adapts. So there might be a gap. There might be a gap between marketing and reality. And I think that gap is kind of a chasm. So I'm not the only person to have noticed this. And in fact, the kernel of the idea that became this talk started about 3 years ago. And it has only gotten worse in the last 3 years. However, 3 years is enough time for even analysts, people who are not technologists, to have started to notice that there are some problems with the marketing versus the reality of these products. And so this is an article on Forbes by someone, and I can't read the text to you because I can't actually see it, but he basically says that machine learning is getting a bad name, and that the CTOs that he's met that are going to these technology conferences are starting to question whether they've been oversold on the idea of machine learning. And the idea is that either they've been oversold on the idea, or the companies that claim they're doing machine learning aren't really doing it to its fullest. They believe that machine learning is still magical and still could do amazing things, but maybe the company that's selling it isn't actually using it right. And they're not sure which, right? Have they just been sold a bill of goods, or is the company that's selling it to them not just doing it completely or not doing it right? And I think this is encouraging because, ultimately it's the people in this room that are the targets of the marketing, right? We go to our respective companies, our respective institutions, and a lot of us influence the purchasing decisions, and a lot of us have influence over what things what services we get bought, and what we end up having to use in our job day in and day out. And if someone is trying to sell you bullshit that's supposedly magical and setting your boss's expectation that you're getting a magical product, and then when you actually get the product and it's not magical, that's a problem. That's a problem for all of us. So this talk is really, oh, and by the way, this is a man carrying a surfboard, according to CaptionBot. So it's really, really, really easy to convince someone that planes fly via magic, right? Because plane flight is really complicated. People learned about the Bernoulli principle and about air pressure and the velocity of air over curved surfaces and that sort of thing. And it turns out that's only like 1/3 of the possible explanations. It's all really, really complicated stuff. And when you're trying to teach something really complicated to someone who has no understanding of it, it's really easy to lead them astray. It's really easy to convince them that there's actually a magical ingredient somewhere in there. And that's what they're trying to do to us. And so I'm going to try to take a little bit of the magic out of it in this talk. So as practitioners, we're typically logical people. We think of ourselves as problem solvers, puzzle people, math people, sciencey people. You know, we're in our families and even in our workplaces oftentimes the sort of the logical person or the analytical person. We typically are not the ones making the final purchasing decisions. I mean, some of us in some of our organizations are, but typically it's the business folks, the less analytical, the sort of the less mathematical, the less technical people that are making the ultimate purchasing decision. And people like us typically are only influencers. And the thing is machine learning actually does some really awesome stuff. I mean, we've seen some really awesome stuff. We've seen computers dream. We've seen some self-driving cars. We've seen them play, certain games really well. And we know that there is some sort of branch of computer science and branch of mathematics and branch of research that's behind machine learning that we're not necessarily experts in. And so it's pretty easy to believe that it can do magical things that we don't necessarily understand because we're smart enough to know that there's some substance there. We just don't know how much substance. And so I want to talk a little about what some of the substance is without getting too technical. This is a blender. And apparently the blender is sad, which doesn't really make sense. I'm not sure why a blender has emotions, but caption bot, there you go. Okay, so this talk is about supervised machine learning. There's really two branches of machine learning. There's supervised and unsupervised. And unsupervised is machine learning algorithms that you give it a set of data and it gives you answers without you having to do a lot of tuning. And so unsupervised machine learning can do things like sort things into categories. And so you could imagine an unsupervised machine learning algorithm be able to sort the people into this room by hair color or by t-shirt color or by height. You know, these are the short people, these are the tall people. And you don't have to do a lot of tuning for an algorithm like that to work. It can just go on the data that it has, find statistical correlations automatically in the data that it has, and tell you we have these different buckets. It doesn't know what the buckets are. It doesn't know these are red shirt or this is brown hair or whatever. It simply says these things are similar and these things are similar and these things are similar in some set of buckets. And there's other unsupervised machine learning algorithms that do similar sorting. I'm talking about supervised machine learning. This is the machine learning that we think of as sort of the more powerful machine learning, the machine learning that gets trained. So that's the machine learning where you speak into the computer and it learns your voice, or you feed it a set of celebrity images and it learns, what a celebrity looks like so it can generate new ones. Supervised machine learning is machine learning that takes a data set in and builds a model based on that data set. And basically every marketing claim that we see about machine learning is actually about supervised machine learning. So this is really a talk about supervised. Unsupervised machine learning does awesome stuff, and it automates all sorts of things, and it can make our lives a lot easier because it can sort through large bins of data and say, it can categorize stuff for us, it can filter stuff for us, it can do really cool stuff, but most people don't even think of it as machine learning, they just think of it as statistics. They just think of it as sort of basic sorting algorithms and basic bucketing algorithms and that sort of thing. So let's make a little bit of sense of machine learning. And so I'm going to talk a little bit about sort of signatures versus machine learning and how some basic machine learning algorithms work. I'm not going to get too technical here. So you have sort of the, if you guys have ever read like a Gartner report, they've got their magic quadrant of, evaluating companies where they've got like ability to execute on one axis and like vision on another axis. And you really want stuff sort of in the upper right-hand quadrant. That's the quadrant where they have both vision and ability to execute. And there's really like, the magic quadrant idea applies just as well to security analytics and processing, right? So you have the blue column is highly specific signatures. They're not very general. And you sort of can get the whole range of fidelity from really low quality to really high quality. The problem is you're writing a signature here, and the signature is not generally based on any sort of statistics or anything like that. So you end up getting something that's really specific. You're writing a signature for just one thing, right? And then, of course, the holy grail is that you have highly general things that will handle large classes of problems, and you also get really high fidelity, really high quality results out of it. That's sort of the holy grail. That's what we're all looking for in our industry. And that's what smart people can get you, though smart people are expensive, and also smart people miss a whole bunch of things because there's just too much data to analyze. They don't have enough time. They have gaps in their knowledge, that sort of thing. And then machine learning, as it exists today in security, typically has sort of an inverse relationship where the more general that you get, the lower the fidelity you get. And so if you want really, really general detection of attacks or detection of malicious behavior or detection of whatever you're trying to detect, if you want it to be really general, you typically also have a really low fidelity, which basically means high false positives or it misses a lot of things. It's just not that good. This is a man brushing his teeth. So if you increase generality, you typically decrease fidelity. One of the reasons is that typically there's an infinite set of data that you could train upon, but there's only a finite amount of data that you can train upon. And this is really important, and I want to talk a lot about false positives and true positives later. You can build a classifier that just flags all traffic as malicious or all events as malicious, and then it will never miss anything, right? It's a perfect classifier. It detects everything. Did it detect attack? Yes. Did it detect no attack? Well, it says everything is an attack, and we know that sort of intuitively understand that that's not useful, because that's no better than just being told nothing. Because if you still have to go through it all, and you have to sort out the wheat from the chaff. You still have to figure out what is actually malicious versus what is benign. And also, 1 in a million in human scale is a rare event, right? If 1 in a million people have a particular disease, then Winnipeg's population, or probably the whole population of all of Manitoba, is around 1 million, right? So you'd expect one person in the whole province to have that disease. But when you're talking about 1 in a million in computer terms, when you talk about like 1 in a million packets, now when 1 billion packets go across the wire, which is a reasonable number of packets that go across the wire, you have 1,000 detections, right? And humans are not good at 1,000. We're not good at 1,000 of anything, right? 1,000 is too much for us. And so with computers dealing with very large numbers, you need 1 in a billion or 1 in a trillion, right? You can't deal with false positives at a very high rate because you quickly get inundated, you get flooded by them. So this is a man taking a selfie in front of a building, which, to be honest, CaptionBot almost got it right here. It looks pretty good. Okay, so there's the 4 combinations here, right? There's the did you detect it or not, and was it malicious or not, right? So if you detected it, but it wasn't malicious, then it's a false positive, right? And if you didn't detect it, but it was malicious, it was a false negative, right? And so you have the true positive, false negative, true negative, right? I think that makes sense. I think people are used to this terminology in our industry by now. Now, people like to use the needle in a haystack analogy. Now, I'm not sure why we use this analogy, because I've been around for 33 years now, and I've never in my life had to search for a needle in a haystack. I don't know who these people are that are searching for needles in a haystack, but we use this analogy anyways. And it's a really poor analogy because you know, the needle in haystack analogy sort of implies that you have a pile of hay and that there is a needle in that haystack. And a needle and hay are different things. But that's not at all the case in reality. In reality, sometimes the hay itself looks like needles. And then you have sort of a needle in a needle stack, you know? Sometimes the needle looks like hay. Sometimes there is no needle. Like you're searching for some event, it just isn't there. And then sometimes the needle's a toothpick. You think you're looking for a needle, but the thing you're looking for is actually a toothpick, right? You know, and these are all much more sort of realistic scenarios that we run into when we're searching for malicious events on our network or when we're searching for attacks on our computers, that sort of thing. Like we are rarely looking for needles in haystacks. We're typically looking for toothpicks in haystacks or needles in needle stacks or other sort of much harder to discern differences between what is what we're looking for and what is not what we're looking for. And then sometimes we're looking and just there's nothing there. We don't have the data. We think there's something there and it's just not there. And so that's a haystack. So I talked about sort of law of large numbers previously. I think this is relatively intuitive. The more of something you have, the more likely rare events happen, right? And we see this, like the lottery is a very good example of this. The chances of winning the lottery are extremely low, yet people win the lottery all the time. Why do people win the lottery all the time? Because millions of people play the lottery, at least in the US, I don't know about Canada, right? So when you have millions and millions of people times a rare event, that becomes a common event. And they sort of cancel each other out, right? The numerator is the number of people doing something or the number of events, and then the denominator is how likely was it. And when those two are large, they sort of end up getting you get a relatively large number out of it. So machine learning classifiers, they are probabilistic. They always have a chance of a false positive, because if they don't have a chance of a false positive, then they're not probabilistic. And we call those things signatures typically. And even signatures usually have a chance of false positive. It's even under like adversarial conditions where someone's like maliciously feeding data, then you can always have false positives, even in perfect fidelity stuff. And sort of the more data you have, the more likely the false positives become. And there's a mathematical theorem called Bayes' theorem, and Bayes' theorem tells you exactly how likely things are. And Bayes' theorem, oh, so this is a toilet sitting in the yard. Bayes' theorem requires sort of three pieces of input. It requires knowing the false positive rate for your classifier, knowing the true positive rate for your classifier, and knowing what's called the base rate. And so sometimes people will call Bayes' theorem, they would call this like the base rate fallacy. And the thing is we typically don't know what the base rate is. You see this a lot in like disease statistics. You know, 1 in 1,000 births are whatever the deformity is, or whatever the disability is, that sort of thing, or 1 in 10,000, or 1 in a million, or whatever. That's the base rate. It says nothing about the test that you're applying to detect this. And so Bayes' theorem allows you to estimate how good is your test given these pieces of data. And so I'm going to run through the numbers. And I know that mathy presentations and going through a lot of the algebra is not the most entertaining thing. So I'll try to do this quickly. So suppose you are building a classifier to detect domain generation algorithms. So algorithms that generate like domain names. Let's just say those domain names are random looking, which is most DGAs generate random looking domains. And so you're building a classifier, and we've got this domain dytheazt.com, whatever, right? And so let's just dump some made up numbers, some statistics about this. So this classifier. So this classifier, when you give it actual generated domains, the domains that were generated via this domain generation algorithm, it'll correctly identify them as generated 98% of the time. Also, they will falsely detect domains that weren't generated by this algorithm 0.1% of the time, so that's 1 in 1,000. And then 1 in 10,000 domains are actually from the domain generation algorithm. So that's the base rate. 1 in 10,000 are actually, let's just say, malicious. We have a classifier that when you give it a malicious domain will tell you with 98% accuracy, or 98% of the time it will correctly tell you that it's malicious, and then 0.1% of the time it will accidentally tell you something that was non-malicious is malicious. That's the false positive. So you plug in the numbers, and I'm not going to go through all the steps. Bayes' theorem it's relatively easy algebra to understand. There's some weird notation like P of the probability of B given A and the probability of A given B, and the notation is annoying, but the actual concept is easy to understand. And when you crunch all of the numbers, what is the probability that the domain is a DGA domain? And the answer is 8.93%. That's really low. I mean, we had a 98% accurate classifier. Why isn't this number 98%? And there's a reason for it, and we can talk a little bit about sort of the intuition for where this 8.9% number comes from. It's much lower than we would sort of intuitively expect until we really think in detail about what was going on, and then it sort of dawns on us that our initial intuition was wrong. So the DGA domains are rare. They're really rare. They're only 1 in 10,000 domains are actually DGA domains, and I'm making these numbers up, of course, right? The false positive rate is 1 in 1,000, but the actual number of malicious domains is 1 in 10,000. And so there's 999 out of 10,000 domains that are legitimate, but when you have 999 or 9,999 domains that are legitimate with a 1 in 1,000 false positive rate, about 9 domains are going to be flagged as a false positive, and only 1 of those domains was actually malicious out of 10,000. And so you sort of have basically 10 false positives for every 1 true positive, which is why the number is around 10%. I simplified a little bit there, but this is really common. So these are this is a group of people riding skis on the top of a building. Okay, so enough with the mathematics and Bayes' theorem. All that was to try to convince you that machine learning is pretty difficult. False positives are a major problem, and it's really difficult to eliminate them. So I'm going to power through some sort of really simple machine learning ideas that work relatively well to classify security data. So I have the 1-dimensional case, the 2-dimensional case, and 3-dimensional case of the exact same idea, just in different dimensions. And this will go to n dimensions. So when you see marketing that says multi-dimensional analysis, they usually mean something like this. They just like to say multi-dimensional because then you think of Star Trek and Doctor Who and that sort of thing, and you don't think about sort of reality. So if you have a set of data on a number line, and you have some events in one category below some threshold, and some events in a different category above that threshold, you just sort of find a point between them, and then it's a simple threshold. Anything above that point is in one category, everything below that point is a different category, and it works sort of in 2 dimensions and also works in 3 dimensions. So I'll show that, right? So the green line is sort of your threshold between the 2 categories in 1 dimension. The green diagonal line through this data set is sort of the divider that you have in 2 dimensions, and then you can sort of imagine a 3-dimensional data set. And there's some plane that cuts through your data that will sort of, everything on one side of the plane is in one data set, and everything in a different side of the plane is in a different data set. And this is exactly how a number of machine learning algorithms work. And so there's something called a support vector machine, and a support vector machine does exactly this, only it just does it in more dimensions, and it finds a hyperplane that divides your data, and it gives you give it input, and it says, okay, well, I think it's in this category because it's on one side of the plane or another. This is simple. This is not magic. When people see this, they go, that's machine learning? And yeah, I mean, that is some simple machine learning. It's not a neural net, but machine learning algorithms that find these planes are machine learning algorithms that apply to real world data, and they work relatively well. They're just not the sexiest thing to market. This is a close-up of a dog. I'm going to skip this because this honestly, this slide is not relevant to the point I was trying to make. But I was talking a little bit about Bayes' theorem here. It's not important. This is a blue and white cake, which for those that are not from the US, this is a postal box. I don't know what they look like in Canada. Okay. Okay. Okay, so sometimes your data is not so clean. Sometimes you can't find a perfect threshold. Sometimes a little bit of your data is in one category but above another category. And so a perfect example of this is the height of human beings. So you can pretty accurately classify people by their height when their height is on one extreme or another. So if someone says this person is 1.87 meters or 6'2" in my case, right? You can be pretty damn sure that person's a man. And then conversely, if they're 1.6 meters tall or 5'2" or whatever the numbers work out to be, you can be relatively confident that person's a woman. But there's that sort of that overlapping layer where there's no clean threshold. At what point is the height clearly a man and clearly not a woman, or vice versa, right? There isn't a clean threshold. And this comes up in data all the time. And so you want to be able to assign some probability. We think that this is a man based on their height with 60% probability or whatever. And there are machine learning algorithms to find that. And so so what I did is I took the exact same data set that you saw in the previous slide, so the blue lines and red lines, and I separated them out into two different axes, and we drew what's called a sigmoid curve between those, and this is a probability curve where 0% all the way at the bottom to 100% all the way at the top, and along the axis, what is the value? Well, if the value is at 50, then you go up the curve and the probability is like 55%. And if the value is over there at like 80, you go up and the curve, it's more like 90%, right? So this is a way of separating data, not based on sort of a simple threshold, but it'll separate data and give you a probability. And so the probability fits the sigmoid curve. And machine learning algorithms, this is called logistic regression. Logistic regression is a little bit more complicated than this, but this is sort of the kernel of the idea for logistic regression, is to find a curve between your data set so that you can say with some probability, we think it's in one category or another category based on curves like this. This is a cake made to look like a clock. Okay, so I'm going to give you guys a real-world example of machine learning, and this is an example from some folks at Cisco. So, as you guys know, that there has been for lack of a better word, an SSL revolution. We are seeing websites and services adopt TLS at a really high rate, and it's fantastic for privacy. It's really, really great for users' privacy. And of course, we've also seen a whole bunch of companies, and some of us probably work at those companies, where the CTOs or the CIOs or the management go, oh my God, SSL, or TLS, it's actually TLS, that kills our security visibility because it's all encrypted. We can't look at it to see if it's malicious. We can't look at it to see if it's an abuse. We can't inspect that traffic because it's encrypted. We have no visibility into it. And so a lot of companies man in the middle SSL, and that actually it sort of trades privacy and even trades some security in the name of security. And when you're trading privacy and some security in the name of security, you're probably doing something wrong. And I'm against this, and EFF is against this, and hopefully most of the people in the room are against the idea of man-in-the-middling SSL. And so a bunch of smart people at Cisco got together. I was not one of them. And they said, well, maybe we can tell if this is a malicious TLS session based on statistical analysis only without any decryption. And so there's a whole bunch of things that go into it. We look at the byte distribution. We look at the cipher suites that get negotiated. We look at the interpacket spacing interval. We look at the size of the messages. We look at the latency. We look at a whole bunch of different things. And as human beings, we have no idea what any of this crap means, but we just feed it into a machine learning algorithm. So a bunch of magic and mathematics ultimately turns into, via logistic regression, draws a curve between a whole bunch of data and gives us some probability out that what we're looking at is a malicious TLS session versus a benign TLS session. So we built this, and I can't read this. So we built this, okay, so when we gave the classifier a known malicious, we know for sure that this TLS connection is malicious. When we gave it to the classifier identified it as malicious 98.92% of the time. So marketing, what Turk calls this 99% accurate. Unfortunately, this is only the true positive rate. And the way that we controlled the true positive rate is we chose the false positive rate. So we chose where on the curve false positive would be. So we set it to 1 in 10,000. And when we set it to 1 in 10,000, the result is that we have a true positive rate of 99%, right? So let's look at these numbers in sort of a real world scenario. Because marketing says 99% accurate classifier, and they just ignore the 1 in 10,000 false positive rate. So, the caption bot isn't sure, but it knows it's food. So I have a picture of caption bot down there. I think that's him anyways. Okay. So, so there's two wildly different ways to market this, right? So Cisco marketing did say 99% accurate classifier, and that's kind of what the paper said too, right? But the paper provides all the technical details where you can go through and you can think about how this would actually work in the real world, right? So there's two different usage scenarios here, right? You can use this classifier, you just send all your traffic to the classifier and it tells you what it thinks is malicious and what it thinks is not malicious. And so if you just run on all the flows, we have to choose some base rate. And so I chose a 5 in every million flows. So 5 in a million flows was the base rate that I chose that said for actually malicious flows. So if 5 in a million flows are actually malicious and we apply our 99% accurate classifier with a 1 in 10,000 false positive rate, if it tells us a flow is malicious, what is the probability that it actually is malicious? And the answer is only 4.7%. And so if you're a security analyst and you get 100 events and only 5 in your 100 events were malicious and 95 of them were not malicious, you're going to say, this is shit. Like, you're going to say that this is a waste of time. The false positive rate is just too high. 95 false positives for every 5 true positives out of 100, that's not good. But if you use it differently, if you hand select some flow that you think you're suspicious about, I'm not sure what this is, you hand select something, then you ignore the 1 in 10,000 rate because you're only applying it to one flow. And then it will tell you there's only 1 in 10,000 chance that the flow you selected is not malicious, or it was a false positive. But if it tells you it's malicious, there's a 99% chance that that is true, right? So two different ways to use this classifier. And this is the way that it gets marketed, as it sits there and it looks at all your traffic, and you get a terrible, terrible false positive rate out of it. Or you use it a different way, and you get 99% accurate, accuracy out of it. And it's the same classifier, just used differently, just marketed differently. And so when you see some of the marketing, think about this. When they claim that they're doing magic, they're claiming sort of this side, and the magic doesn't work in reality. But when applied, when you're aware, when you're cognizant of the limitations, and you are careful about how you apply it, you can get really good usage out of it. This is a cat wearing a tie. Yeah. Okay, so machine learning, it can be incredibly useful if you're careful about how you apply it. And all those problems that I showed you in the beginning, they were all based on grid-like data. They're all based on image data. They're all based on audio data. They're all based on two-dimensional grids. What problem in security is a two-dimensional grid? Like, we deal in logs. We deal in network traffic events. Like, very little of our data is two-dimensionally gridded. And we can sometimes massage some of our data into a two-dimensional grid, but that's oftentimes really stretching it. So many of the amazing revolutions that we've seen in neural networks and generative adversarial networks and other cool pattern matching just doesn't apply to the type of data that we have in our field. And so almost all of that stuff is just marketing crap. So, you can use machine learning, you can couple it with signatures. I'm running out of time here, so I'm gonna skip over some of this, but it can be very useful, but you have to be sort of very cognizant and wide-eyed and really think about, are we using the technology in the way that it should be used or the way marketing wants it to be used? Because marketing doesn't understand false positives. Marketers, they don't understand when you're going through 100 events and 95 of them were false positives. They don't understand that that means the product is useless. But they'll market it as though it's a 99% accurate classifier when the reality is it's not actually useful to you. So I have 1 minute. Can we squeeze any questions in a minute? Okay. Does anyone have any questions? Yes?
Yeah, I see what you described here is very good what you do with Cisco, modern network traffic.
Yes.
But I look at it as a faceted problem because why do you have security breaches? It's not because we didn't get a sophisticated tool. It's because the password is still password.
Yeah, you're right. So, but if someone is trying to sell you machine learning to tell you your password is password, you're being sold a sledgehammer to squash a fly.
So, I'm just wondering whether companies sort of create this sort of problem because we're out there employing machine learning and really what we should be packing down there and change your bloody password.
Yeah.
Turn on your RTO.
Yeah, I completely agree with the point you're making, and I think to summarize what you're saying, the fundamentals really matter. And we might want to go after the new shiny things. We might want to go after, you know, the really cool tools and the really hard problems and the really sophisticated attacks. But our time is probably better spent on the fundamentals, like making sure that the password isn't Cisco 123.
Not nearly as hard as you're describing. I'm saying that Cisco's job is that tool. Absolutely. It's people are buying Cisco tools, they fall change the password.
Yeah, I'm not sure that it's necessarily Cisco's job or any other vendor's job to really, you know, good password hygiene is sort of our job as security experts and security practitioners in this room. Like when someone asks, when someone has no security and they ask, what should I do? I have no security right now. The answer that comes from the people in this room should not be buy whatever the product is. It should be stick to the fundamentals first, get the fundamentals under control, and then once we have the fundamentals under control, maybe we can focus on some of the harder problems. But still, like if we're looking for some magic machine learning product solution from Cisco or any other company, we're probably not really thinking very well about what the actual problem is and whether or not what's being sold to us is actually going to work. Thank you for your time.